So this is the example that we have. Use a cyclone separator to separate solid kaolinite powder with equidistant PSD mesh between 0 to 50 micron with 25 intervals. So it is a equidistance model with 0 to 50 micron. The powder is having standard deviation of 5.227 micron and mean 8.343 micron. So the particle size distribution of the feed has been given. The flow consists of 1000 kg of kaolinite and 10,000 kg of air. So 10,000 kg of air per hour. So you can understand at what speed that is flowing. Okay, very high speed. The temperature and pressure are given like this: 30 degrees centigrade and 5 bar pressure. 5 bar is huge pressure. Okay, 5 times the atmospheric pressure. So with this pressure, the flow is entering into the vessel, the cyclone vessel. Study the particle size distribution of the top and bottom products of the cyclone. That means they are asking you to find out the particle size distribution of the bottom and the top. That means whatever is the finer particles that is going above the top and the heavier or larger particles going through the bottom. So both you have to find out. They have given 3 conditions. In the first condition, you have to simulate the cyclone separator with user-specified dimensions and calculation method. I have a set of data, user-specified data, which I will show in few minutes from now. So that data I will use user-specified dimensions and calculation method. So we have both dimension and the efficiency curve. Now, the second problem is design the cyclone separator to achieve exactly 75% separation efficiency. And they are giving a maximum allowable pressure drop also. Pressure drop should not exceed 0.015 bar. Okay. So it should not go below 5 bar minus 0.015 bar, or whatever it may be. So the pressure should not go beyond that. Otherwise, there will be a problem in the cyclone separator. In the same breath, they are asking, how do you stretch it to 80% separation efficiency? So first you have to design it to 75% and then you have to redesign it with 80% separation efficiency requirement. And finally, you have to redesign the cyclone with other standard calculation methods and types and compare the results. That means you do not use the user-specified thing. You can use that Leach or Maschalk-Knaus, the other separation efficiencies that we have found. Okay, we can use them. So let us go one by one. So go back to the Aspen Plus window. So in the properties, we have to provide these 2 things. First is kaolinite. So this is kaolinite powder. So let us find kaolinite. Yeah. So we select. Let us rename it as kaoline. And then air. Kaoline will be solid. Air will be conventional. And then we choose the method. Let us choose solid model. Run. Okay. Now go to simulation model. in the flow sheet, let us rename them. Let us rename it as feed. Let us use it as top and bottom. And we have to provide the feed, but before that we have to set the particle size distribution and stream class. So in the particle size distribution, let us see, it is equidistant PSD mesh between 0 to 50 micron with 25 intervals, right? So we will go over here, we'll find equidistance (25) from 0 to 50 micron, create PSD mesh. Okay, and choose the stream class to be mix CL PSD. Right. Now we are ready to give the feed. So this is flow consists of 1000 kg of kaolinite and 10,000 kg of air. And temperature and pressure, they are 30 degrees centigrade and 5 bar pressure. So let us, this is 30 degree, 5 bar, and $10,000. And go to CL solid. (30 degree), 5 bar, (1000 kg). And you have to give the particle size distribution. In the particle size distribution, you have to provide the distribution function in micron. What are the values? Standard deviation 5.227, mean is 8.343. So 5.227, 8.343. So it is 5.227 and 8.343. Calculate. Okay. So inlet particle size distribution has been given over here, and you will find that there is hardly any particle above 25 microns. So although it is saying that the particle size distribution is from 0 to 50, but within 0 to 25 itself, all the particles will be there. It's spread over this range. Okay, so feed specification is done. Now let us go to the actual thing, the input. Okay, so simulate the cyclone separator with user specified dimensions and calculation method. So we have to do the simulation, user specified and user specified. So user specified dimension and efficiency. Both we have to give. Now here in dimension, you have to give the actual length or actual length. Unlike the ratios, in ratios we had to give the ratio of the length and the diameter of the bed. But here we have to give the actual length, so actual dimensions. Okay, so we have to provide this data. So this is the example, and this is a commercial product, okay, available in internet. So I have gathered the information from there, and I have masked the name of the company for obvious reasons. But you can get all the information that is needed. You can see the schematic of that particular Cyclone that they sell. And you can see this is a rectangular inlet. Here it is the Cyclone, and this is a vortex. This is the discharge of clean air. Although they are saying clean air, but there will be some particulate matter in it. And this is the exit for dust or the material discharge, that is the solid material. And the clean air moves upward to the center in this way. You see as it is directed over here. So this is the movement of clean air. It goes like this and it exits through this channel. Okay, that's how the product operates. You will find a table specification. So size A, this is B, C, D, E, F, G. So this matrix has been given. So this is size matrix. What are they? Let us check further. A, B, C, D, E, F up to V. Here, you see, this is A. This is A. You remember? Diameter of the column. Everything depends upon the diameter. All the ratios and all. So A is the diameter. And here it is B. B is the length, total length of the Cyclone. Then C is the dimension of, that is the length of conical portion. D is the length of the cylindrical portion. K and L, they are the height and width of the inlet channel. So all the dimensions are given here, and they are tabulated over here. So from this tabulated data, you can get the information that the company has 10 different sizes of Cyclone separator. And the smallest one is having a diameter of 29 inches, and the larger one is having a diameter of 74 inches. Okay, and based on the diameter of this, all other dimensions are given over here. So this is one size example. This is a different one. This is a different one. This is a different. So there are 10 such Cyclone separators are there, and dimensions of each Cyclone separator has been given in this table. Okay. Now let us find out what is the efficiency curve. Here you can find the efficiency curve. Let us make it a bit bigger in size. Here you can see the size is from 0 to 100, right? So 0, 10, 20, 30, 40, 50. Now in our problem, we'll use up to 50. This is up to 50. This is the curve that we are looking for. So basically, in order to obtain this curve, we can find out these data points through experiments and obtain this data curve. Now, in order to use this information in our simulation model or design model, we have to extract that efficiency curve. Now, I have done it myself and I have the results with you to show. So you can just see this. So this is the efficiency curve, size in micron and the efficiency in percentage. So this is the efficiency, and I have developed the efficiency curve. You can compare them. And these are the data that we will use in our simulation or design. And they have been taken from this particular model. This model, 29 inches. Okay. So our diameter is 29 inches. What is the length of cylinder for them? Length of cylinder is 41 and half. Just check. This is 41 and half. What is the diameter of overflow? It is 7.5. What is the height of inlet? It is 14. Width of inlet 6.5. So here you see K and L, 14 and 6 and half. 14 and 6 and half. It is KLN, right? Let us cross check. Yeah, this is K and L. So we have gathered all the necessary information from the Cyclone separator that has been given in that particular sheet. So I have taken the lowest dimension one. You can use the other 9 models at your will for a practice. Okay. So this information we'll use. So we have to do this simulation. Okay. Now let us go back to our Aspen Plus simulation. So we have to provide the dimension. So let us first convert everything into inches. Okay. Length of cylinder is 41 and half. Length of cone section 38 and half. Length of vortex finder is 22.5. Diameter of overflow, it is 7 and half. Diameter of underflow is 6 inches. Rectangular inlet. There are options for round, axial, spiral, but we are using rectangular inlet from the example. It is 14 inches and this is 6.5 inches. So that covers the dimension. Now efficiency. Efficiency. So you have to provide all those data. So you just can copy and paste over here. Right. Now efficiency, we have to give it in fractions. So what we do, we shall write this by 100. And then copy, paste. right? So efficiency has been given, and we can give the diameter. Diameter is 29 inches, right? Diameter is 29 inches, so we write 29 inches. So now required input complete. Now we can simulate. So simulate. Okay. So results are available. Let us see what are the results. For that, go to the stream results. So out of 1000 kg of feed of kaolin, 781 kg is coming at the bottom, 218 kg is going through the top. Okay. And air, everything is going through the top, right? What is the CLPSD substream? Open PSD. So as usual, there is hardly anything below this point because we found that our input PSD curve was finished within 25 to 30 micron range. So above that, we'll not get anything anyway. But within this range, the top product contains mainly the finer product. Okay. And the higher range particles are not found that much in the top product. Now you see the efficiency is 78% and pressure drop is 0.05 bar. Now we have simulated based on whatever the data we have gathered from that product, right? So actually it is a real life experimental product that we have obtained. And this is giving us an efficiency of 78%. And the pressure drop is 0.05 bar. And the dimensions, exactly what we wanted, is 29 inches. This is 41 and a half. Okay. Everything as per what we have given. But in the next problem, they're saying that let us design it so that 75% efficiency is obtained. So he is saying basically that 75% efficiency is sufficient for us. There is no need to go to 78%. Rather, you limit your allowable pressure drop to 0.015 bar. Here the pressure drop is going beyond 0.015 bar. So it is asking us to limit it within 0.015 bar. So let us design. And obviously, in a redesigned condition, it will no longer be 29 inch, but let us see what happens. So for that, let us go back to input and we have to design. In design case, you cannot give user specified. So if you give user specified, then it will give an error. You have to give ratios. Okay. So you have to specify ratio. Now you have to provide 0.75 efficiency and maximum pressure drop 0.015. But the ratio that you have to choose, length of cylinder will be 1.431. So now these ratios I have obtained by dividing these numbers with 29. So everything divided by 29. So this one is E3 divided by 29, E12. This one will be E4 divided by E12. Like that, E10 divided by E12. Okay. So these are the ratios that we have obtained. The first one is length of cylinder. The ratio we have to give 1.431. Diameter of overflow, it is 0.259. 0.259. Length of cone section, 1.328. 1.328. Diameter of underflow, 0.207. 0.207. Length of vortex finder, 0.776. 0.776. Height of inlet, 0.483. 0.483. And width of inlet is 0.224. Okay. And the maximum diameter, we have to set something because it is going to design, right? So it will no longer be 29 inches, but allowable maximum diameter will be something higher or lower than that. Now, we want to limit ourselves to 5 meters. We do not want cyclone separator having a diameter higher than 5 meters. So that limit we are giving to the Aspen class so that it can calculate accordingly. Okay, so all inputs are completed. We can run now. Okay, results are available. In the stream results, we'll find some particle size distribution. We are not that much worried about it. Let us go to the results. Cyclone result, you see, efficiency exactly 75%, whatever we have obtained. But the pressure drop, it has reduced to 0.008, below 0.015 bar, right? We asked them to calculate below 0.015 bar. So it has calculated 0.08008 bar. So it meets our criteria. And the diameter it has calculated to be 45 inches. 45 inches. So it is no longer 29 inches. It is higher than that. Accordingly, the length of cylinder has been calculated to be 64 inches. Right. Now, what is the ratio of length by diameter? It should be 1.431. So if you do this calculation, that is 64.7449 by 45.2445, then you will get 1.43. Okay, so they have designed this diameter of the cylinder, and accordingly all of them have been calculated based on the ratios that you have provided. Okay. And some other things they have calculated, like inlet saltation velocity ratio, axial inlet gas velocity. So all of them they have calculated accordingly. Now they have asked us to stretch it to 80%. So they are saying that we are not happy with 75%. Let us stretch it to 80%. So simply let us design it or redesign it rather and run. It is showing some error, right? So check status. What is the reason for error? The following unit operation blocks were completed with error B1. It is saying the pressure drop is 1917 and maximum is 1500, because we have taken 0.015 bar, that is the maximum allowable pressure drop rather. So 0.015 bar means this much of Newton per square meter. Okay, but it is going beyond that, so it is not permissible. That is the reason. So the question is, how do you stretch it? Now, if it is allowed, let us try with a slightly higher pressure drop. So let us increase the allowable pressure drop to 0.02 bar and let us see whether it works. Yes, it works. So you see the result summary once again. So we get 80% efficiency and pressure drop is 0.019 bar. So it is still below 0.02 bar, so it is acceptable. Okay, so one thing that we understand, that if we stretch the efficiency further and further, it is possible, but then pressure drop will also be higher. So it may not be acceptable for the system. Okay. Finally, we redesign the Cyclone with other standard calculation methods and types. So other calculation methods means use something else. Say use Marshall-Knauss model, and ratio you can use a Stearman-H. Design pressure drop, limit it to 0.015 bar and see what results you get. Now when you choose them, obviously dimensions and ratios, efficiency, everything is off because they are not needed. You are not using your own user specified stuff. You are using whatever Aspen has got in its model bank. So they are obtaining them and using it. Anyway, the results are available. You can check the results. You get 98% efficiency within this pressure drop. Okay, but accordingly, your cylinder diameter will be 28 inches. Okay, and length of cylinder will be 1 meter. So in inches, it will be 43 inches. So using Marshall-Knauss calculation method and Stearman type, they will have different diameter, different length, the cone angle will be different, etc. So you can play around with other models like this and other types of cyclone, and you can practice. Now, let us work with solid separator. Now, in solid separator, as before I told, that it is just algebraic manipulation. For instance, in the solid separator, you can opt for conditions. One is either solid load of vapor outlet, vapor load of solid outlet, or fraction of vapor to vapor outlet. And you can give one of them, that is fraction of solids to solid outlet and fractions of vapor to vapor outlet. So fraction of solids to solid outlet, ideally it should be 1, but it will never be equal to 1. We may say that we want 99% of solid will come through this. So this figure we can say 0.99. We want that. So do the calculation accordingly. Similarly, solid load of vapor outlet. Ideal condition, the solid load should be very less, right? But absolutely it cannot be 0. So let us say it is 0.05. So this figure is 0.05, this figure is 0.99. And let us check what happens. So let us check fraction of solids to solid outlet. Let us use 0.99. Solids load of vapor outlet, we can use 0.05. Now, classification characteristics, you can either give particle size or particle settling velocity. Separation sharpness and offset of fines, you know what they are. Let us give separation sharpness of, say, 0.5, offset of fines 0, and pressure, outlet flash specification. Pressure, let us give pressure drop of 0.015 bar, and let us run. So the calculation is done immediately. Let us see the results. Now PSD is not that important here. Now here you can see what was the option for us. Solid load of vapor outlet should be 0.05. Let us check. What is the vapor outlet? Top. And what is the solid load for this? 9.9994. So almost 10. 9.99945 by this one. 209.999. You calculate it. How much do you get? It is 0.0476. So almost 0.05. Okay. So that is the solids load. And the other one, that is fraction of solids to solid outlet, it is 0.99. Let us check this one by this one. So 990.001 is equal to 0.990. With that, we come to the end of this lecture. I hope you have enjoyed it, and we'll come back with yet another interesting lecture very soon. Thank you.